Okay, so Rick is referring to the symbol. It's a little box symbol. It's in the 288 constants of nature. Let's see, physics, monastery. I swear I can spell. Thank you, autocorrect. Yes, you visit here often. All right, so let's share the page. No. I swear I know how to use this thing. All right. So that's basically the inversion boundary. To be fair, that's a good question. I don't even know if it has a formal name. It's literally just the inversion boundary. It was originally 10 to the minus 7, then went to the monastery. I'm doing the calculations. I'm like, all right, it's really close to 10 to the minus 7 using the numbers that he had derived for the claimed closed forms for the different Planck constants. But it wasn't 10 to the minus 7. It was like 0.99999999 times 10 to the minus 7. So it's really close. And to be fair, even with the, I think they had it originally defined. It was like the magnetic constant or something, because it's technically Ampere's constant, stripping out the dimensions. Let's see. Hold on, symbol legend. Okay. So it's the hyperbolic inversion boundary. It's this little box. It just used to have the plus sign there. Now he's kind of using this, and Casey has brought up that I think within mathematics and stuff that is a used symbol, but that just kind of using it because it's kind of like the cone of your space-time diagram within a box. And the claim is that something interesting is going on here, maybe around that 7th significant digit, because again, the quote that is often misattributed to Lord Kelvin, which technically came from, I think, Michelson from the Michelson-Morley experiments, which isn't even an exact quote. It was paraphrased as the future in physics simply lies within the determination of the 6th decimal place of accuracy, aka we know physics, it's basically done. We just need to get increasing precision. Okay. Now that may have actually panned out, except as we got more precision, things started to get really wonky. And a lot of that wonkiness seems to happen around the 7th significant digit. Why? Also, there's that whole pesky uncertainty in the gravitational constant, because, well, we've only really got that down to about 5 significant digits, and that's when we're constructing our Planck units. We're usually using big G, h bar, and c, the speed of light. Okay. Speed of light, we have to 9 significant digits. H bar is literally now defined at 10 significant digits. Okay. The problem with big G is if you got like half the significant digits, what are you gonna do? That's, oh, sorry. Oh, I was making sure I was still talking. Oh God. There we go. I just wanted to make sure it was actually broadcasting there. Yeah, so it's the hyperbolic inversion boundary. HIB. If anybody's got a good name for it, totally open, and I'm sure Thad would appreciate it, because that's literally just the claim. And as we can see, it's can we minimize? Nah, it's not gonna do the little thing either way I want. Oh well. Okay. Oh God. All right. So basically, the whole thing is that box is equal to Planck length times the Planck mass divided by the Planck charge squared, and then we're literally just taking the units and inverting them to cancel them out. So we get a dimensionless number. Now you can say that is a reckless thing if you accept that maybe there is some significance, or again, this is something a lot of folks can argue with, and again, there's a lot of valid argument there. We're almost instantiating a preferred unit basis. Why, baby? That seems crazy. If we're willing to entertain that, some very interesting things that can be done. At least I would claim. Now, again, I'm very biased on that, but it is the that calls it the hyperbolic inversion boundary there. And if basically if you just take all that Planck length, Planck mass, divide by Planck charge squared, Planck mass, Planck length, I'll divide by Planck charge squared. It's going to give us Ampere's constant. Okay, as we can see, it's estimating here 10 to the minus 7, aka it is Ampere's constant, which is also, what's this? Oh, it's 1 over 4 pi magnetic constants, because just do 1 over that, you're going to find, oh, look, 12.56, blah, blah, blah. Oh, look. Oh, it looks like 4 pi. Now, I realize I did that very fast. The only reason I'm able to do this is because I was confused as heck for a while. I made all these mistakes, but going through and making mistakes again, and then eventually getting things right and going through doing some calculations, it's almost like that thing that they told you in school to do practice problems might actually be useful. Now, again, I understand. I can go into the modern chat or a lot of these agential things. I can ask you the question. You can set a Lagrangian, do all this calculations and stuff like that. You can do it really quickly in things that might take me an hour to set up in Mathematica. But it's kind of gaining that whole intuition, like what might actually happen. Or when you make a mistake, and also, let's face it, if everybody makes mistakes, if there's a really complex calculation, you're just trusting it. It's like, are you sure? Now, again, there are modern tools to help clarify this, such as, well, actually, there's a Wolfram tool that we're technically supposed to send out for computation. Yeah. Okay. That was a very long-winded answer, but let's continue. Where are we? All right. Very cool. Yeah, no. This is the other thing I've realized. It's if you're trying to do something and pay attention to something else, depending on how ingrained and natural that thing is, it's going to throw you off. Because like if I go out for a run, if I'm trying to listen to like a high-level lecture where there's lots of stuff that I don't know, like if I'm listening to Stephen Wolfram and Jonathan Garrod go back and forth about high-level topics, I've literally put those on and immediately fallen down. I'll go be running, I'll miss something, and I'll trip. If I put on a whole bunch of just random anime music, maybe not much, if any, lyrics that I even understand, but I'm used to, usually fine. So it's interesting that we seem to have a fixed amount of consciousness we can apply towards different tasks. So that is interesting. Oh, inversion boundary with Ampere's constant. Yes. All right. Well, the inversion boundary it's literally Ampere's constant minus the dimensions. So we'll just take this, divide it by Ampere's constant. Should get 1. Guess it's 1. So yeah, it's and again, even I was going through, I'm like, wait a second, now wasn't it 10 to the minus 7 by definition? But you look at it, I only know just because I checked this the other day. Magnetic constant, CODATA. Let's see. No, this is the 4 pi version. Hold on. Magnetic constant. Okay. So that would mean Ampere's constant is also fine structure constant, h bar, elementary charge, speed of light. All right, so let's I'm gonna move this out and just so I can have it in front of me. Give me a moment. Wolfram alpha. So let's do this. Actually, I haven't done this calculation before. Fine structure constant, h bar divided by elementary charge squared times speed of light. Okay, and that gives us Ampere's constant. That is interesting. Oh, thank you. I did not know this relationship. I'm assuming since it's elementary charge, and then the fine structure constant is over there. It's doing. Let's duplicate this. Let's just take this out. Take this out. Is this going to be? Oh, okay. So this is. See, I know if I take the square root of this is going to be the Planck charge squared. I'm pretty sure. Let's, or if I take the square root of just alpha. Oh, let's just do that. Okay, and then we take the square root of the whole thing, and this should be the Planck charge. No, I was wrong. It's wrong dimensions. Oh, what if I invert it? No, I'm off. Do I not take the square root of that? Oh, it's gonna, okay. Oh, okay, I just need to invert the first time. Okay, so okay, that makes, okay, duh. Because if we rewrote this whole dang thing, just elementary charge squared over the Planck charge gives you the fine structure constant. So if you're going to do it the other way, then it's just going to come out this. All right. Okay, so this gives us the Planck charge squared because it's times 10 to the minus 36. Planck charge is to the negative 18th power. There we go. All right. This is interesting. Fine structure constant. All right. So if we take the alpha of the elementary unit of action, we divide it by the elementary unit of charge times the speed of light. We got mass. Okay, because that's got mass. Mass, it's 2 speed of light is taking off 1 dimension of length there. Hold on, we got a board for this. All right, let's see. Just keep track. All right, so we've got oh god, this is I take a random paper towel to. There we go. There we go. All right. There we go. All right. A nice semi-clean board. Or a semi-coherent AMA, am I right? All right. So we got alpha H bar. Hold on, I need to write this out. Alpha H bar. Blah, blah, blah. Elementary charge squared. Let's see. All right. So this is dimensionless. This equals. All right. Planck units. It's Planck mass. It's Planck length squared. So L sub P squared. That's 1 unit at a time. So Planck time. Elementary charge is I can't do that. Oh, that's alpha. Oh, it's canceling out there. Okay. Ooh. Okay. So that'd be Q sub P of electron. All right. So charge. No, charge minus charge. Okay, so no, elementary. We're just going to do elementary because it's not specifying positive or negative squared, and then c is the speed of light. So, all right. So c, we're going to divide out 1 unit of length. And this is we're going to divide out 1 unit of time. Okay. So the speed of light ends up canceling out that second dimension of length because we're dividing by c. So numerator c is length divided by time. So we cancel out 1 dimension of length, 1 dimension of time. And okay, and then with alpha, this makes this the Planck charge. Oh, cool.